Okay, welcome back. So this is part two of my review of Clayton's book, Bernoulli's Fallacy. So what's mentioned a lot in the book is what we really want is the probability of hypothesis given the data. And I don't think that's always I don't think that's always true, first of all. Second, you're not really getting the probability of hypothesis given the data. It's more like with Bayes, you're probably getting like probability of hypothesis given the data and a bunch of assumptions or beliefs. So I wouldn't really call it a probability in some cases. But this whole idea is like what we really want is X. And then X happens to be like 100% aligned with the statistician's philosophy or something. That's called the statistician's fallacy by Lakins, and I think it's really common. I mean, this phrase must have been repeated a bunch of times in this book. You could argue the other way, that what we really want to say is our procedures have good performance. They're reliable, we know the error rates, they're free from as much subjectivity as possible, and we're not confined to try to solve all problems with the same tool. We have a flexible approach. We can try different things instead of just saying Bayes theorem or something. So you could easily just say that, you know. The book has a section on the Monty Hall problem. I have a little article here that talks about it, and you don't have to refer to Bayes whatsoever. You can, of course. There's several different ways you could solve it. I personally, I'm pretty empirical, I guess. I like the simulation approach. Clayton, in his book, just outright rejects the simulation approach. But I found a video where Clayton talks about how approximations are great and who needs analytic solutions anyway. So if he wants to accuse, or Jaynes or whoever wants to accuse frequentists of being ad hoc, then he shouldn't be ad hoc, right? Um, it's simulation works well. You can just list out the sample space. Let me just open up my article real quick, a little web page. You can just list out the sample space, okay, and kind of reason from there. You can also do simulation, as I mentioned, and you can also do a diagram, truth table. There's many ways to solve this problem, and you don't need Bayes for it. You could use it, of course, but again, it's not really what I would call a Bayesian problem. It uses Bayes' theorem, which is frequentist. So I have a section on proofs of God. I won't read this whole thing, but basically, with Bayes or frequentism, you can come up with proofs of God, proofs, and they're very they're full of fallacies. I mean, it basically, like most things in Bayes, it rests on your assumptions. So I have an example of a frequentist proof of God. I have an example of Bayesian proofs of God. And arguably, though, the Bayes ones could be maybe more justified because, especially in this totally subjective version of Bayes, um, they're not convincing. You're kind of just saying, here's my strong prior, and I might massage the input data, and I get a large posterior at the end. So it's not they're not very convincing. But now he has a section, Sherlock Holmes was Bayesian or something, and therefore you should be too, I guess, is the argument. I don't really care because he's fictional. Now I'm a very strong believer in Sherlock Holmes. I have the tattoo, right, to prove it. Okay, but he said stuff. I would say from likelihood school, frequentist school, and Bayes school. Again, I don't really care. I just thought it was funny to have that in a book. Um, you know, I don't know. It's funny. Okay, so testing ESP. So I think Clayton tries to use the argument of like studies purport to show evidence for ESP. ESP's bunk, therefore frequentist methods, since they were used, are bunk. Okay, but that's a bad argument. Like you could do the same thing again with Bayes factors or any posterior probability or any prior that you decide to use. Now, first of all, I have a section on James Randi Educational Foundation here. They had $1 million challenge for years testing ESP and dowsing and stuff like that. So if ESP claims were true, you would, in a frequentist approach, you would lower your alpha drastically, so no one would win by chance unless they actually, I mean, no one would win unless they actually had the skill, right? And you wouldn't do the experiment once, you might repeat it a couple times to make sure. Well, needless to say, no one ended up winning this challenge because, well, presumably they don't have any of these skills, dowsing and so forth, that they claim to have. But they rightly recognize that, you know, if that stuff was true, it would change our knowledge, our fundamental knowledge of how the world works. So it makes sense to lower your alpha in that case, right? You wouldn't just use this kind of quote can default of 0.05 because someone could theoretically win it by chance, even though that would still be somewhat unlikely. They could, even if an experiment's repeated, they could possibly do that. They could possibly win several times in a row. Now, Bayesian approach wouldn't solve this. It's always portrayed as, oh, the Bayesian approach, because the frequentist had a failure, the Bayesian approach would automatically solve it. But most of the times they're kind of equivalent in a sense. In one ESP study, it was said Bayesian results range from confirmation of a classical analysis, i.e., frequentist, to complete refutation. It just depends on the choice of prior. So, how are the priors chosen, and who chooses them? Is that issue here? In any case, obviously you need more than just significance or an effect, or just that there is something there. You need to know how big that something is. You need practical significance too, which you can get from frequentist approaches also. If someone claims to affect the outcome of a coin and it's statistically significant, but you're getting only maybe like 2 more heads for every 5,000 flips, is that of any practical concern? Probably not. So you need to know practical significance, and this has been drilled into me since grad school. So now he has 9 problems. I found these problems frankly underwhelming and not really any problem for frequentism. Talk about base rate neglect, malfunctioning digital scale, sure thing hypothesis, optional stopping, problem of divided data, German tank problem, testing for independence, the lucky experimenter, and finding a lost spinning robot. I won't go over all these, but I didn't find any of them really showing any problems with frequentism per se. And, like the base rate neglect is, again, we're just working with the standard base theorem here. Malfunctioning digital scale, you're kind of blindly following any approach. I didn't really find any of these. Some of them were very contrived. German tank problem, both methods work pretty well. I think the frequentist one's easier to do and explain in that one. So I don't think that's a really great advertisement for Bayes, in my opinion here. For 2x2 tables, tests of independence, which of the methods a researcher uses depends on assumptions and goals. Everything gets dismissed as ad hoc, so there's no point in saying it depends on your assumptions and goals, but that's ad hoc. I guess apparently there should only be one way to do 2x2 tables. I don't know. So one thing, I have this section on notable omissions, and if you read anything of my review, please read this section, because so Clayton, the too long, don't want to listen or don't want to read version is he oversells Bayes and undersells frequentism. So he doesn't mention some things about frequentism, which just goes to show that looking at data that did not occur is important. Looking at the counterfactual stuff is important. He doesn't mention equivalence testing. This would be a way to get at the smallest effect size of interest. So read up on equivalence testing. You can reject the null hypothesis and fail to reject the null of equivalence. You can reject the null and then also reject the null of equivalence. So you have the 4 different interpretations over here, depending on if something's there or not. So you got 2 choices, kind of reject or fail to reject the null hypothesis. And if it's of the size you find meaningful or not. So that's the smallest effect size of interest. So this is a great way to go about your hypothesis testing. because it takes statistical significance into account and it takes practical significance into account. He doesn't mention severity. Again, this is in Deborah Mayo's book. So this is about looking at, formalizing Popper's notion of thoroughly testing a claim. So with Bayes, you can assign, well, let me back up a little bit. In frequentism, you can have an approach of like a long-term error rate. In Bayes, you can just assign probabilities. But we're really interested, most likely, if has a claim been thoroughly tested. And so severe testing kind of does that. It's kind of like an attained power calculation. So read up on that. I think it's very, very, I don't know. I don't want to say shameful, but very bad that was left out of the book. I think it's very, very important. Same thing with confidence distributions. Clayton mentions Fisher's failure of fiducial probability, but he seems just unaware of its modern development. So that's in this book. So they take fiducial distributions and put it in modern terms and stuff, and it works. So I think that one is a big omission. And Efron has said, here's a safe prediction. I believe there's a good chance that something like fiducial inference will play an important role. Maybe Fisher's biggest blunder will become a big hit in the 21st century. It kind of ties frequentist, Bayesian likelihood, all that stuff together. So it represents confidence intervals for all levels of parameters and interest. And you can solve some pretty interesting problems, and you can update likelihoods, and you don't need priors. He talks about the American Statistical Association's position on p-values. So now I don't hold this against Clayton because I think his book was probably done before they came out with their third statement or whatever. I have them all here, links. So the first one just said don't only rely on p-values. Okay, so I really don't know in practice who was doing that anyway. Like only looking at p-value and saying, okay, we're done. The second one was interpreted as don't do this, and kind of interpreted as being like an official statement or something. It had a lot of problems with it. There were alternative approaches, but the pros and cons weren't really addressed. There was some weird coordination with nature and getting signatories to, and they got 850. I mean, I think if you got signatories for using frequentist methods and or hypothesis testing, you'd probably be in the magnitudes more than that. So I just thought it was bizarre. And the third one, they just kind of say, well, it's okay to use p-values, use them correctly or something like that. Phew. But after two, even after one, I mean, you just look in the literature, people are still using statistical tests all over the place. And I think you have to because, or you're using something like it because you're assessing what you expect under a model versus what you observe from a test statistic. And you're assessing essentially that distance between them. If you want to put that in probability terms, which is a p-value, that's fine. But it's basically assessing that distance between what you expect under a model and what you observe. So I don't see how people can get away with that, personally, without doing something like that, even if you're doing it behind the scenes. Clayton, in his book, quotes, I don't know how to say this name, Ionides, work on the number of false positives. But that author, he also wrote, statistical significance sets a convenient obstacle to unfounded claims. In my view, reviewing the obstacle could promote bias. Irrefutable nonsense would rule. Yeah, if you don't have a basic hurdle. Murtaugh, he was actually one of my professors at Oregon State. He wrote In Defense of P-Values, where he links, he notes that if you want to get rid of p-values, it's kind of, or maybe I say this, I forget if he said this, but it's like saying, use Fahrenheit over Celsius because Celsius is bad or something, right? They're all related. So p-value, Bayes factors, AIC, BIC, confidence intervals. You could, if you consider p-values corresponding with Bayes factors, values of Bayes factors, just saying p-values are bad, the same exact arguments could apply to Bayes factors or anything else. If you have arbitrary cutoff you're using no matter what, if you have hard rules that say if your Bayes factor is greater than 20, reject or something, and then you get 19.99 or 20.01, right? You can have the same exact stuff. So I have just a discussion of that here. BASP was mentioned, the journal, Basic and Applied Social Psychology. They got rid of p-value statistical significance testing. So it's one thing to get rid of it. It's another thing to ask, did the science improve because of that? And there's been several assessments, discussions that, we found multiple instances of authors overstating conclusions beyond what the data would support if statistical significance had been considered. So it didn't improve, at least at this time. It did not improve. Lakens has a discussion on that, and Hand has a discussion on that. Bayesians can stop whenever, I write just because one can doesn't mean one should. And stopping rules matter too. Steele writes, if a drug company presents some results to us, and they say, a sample of N patients showed that drug X was more effective than drug Y, and this sample could have had a size N fixed in advance, or had been generated via an optional stopping test that was stacked in favor of accepting drug X as more effective, do we care which of these was the case? Do we think it is relevant to ask the drug company what sort of test they performed when making our final assessment of the hypothesis? If the answer to this question is yes, then the Bayesian approach seems to be, wrong-headed or at least deficient in some way, right? If the stopping rules, if you can stop whenever, then you shouldn't really care which one happened here. But I think in real life, we probably would if it was, optional stopping, and the company said, "Okay, we reached the results," and they just stopped. There's another one, why optional stopping is a problem for Bayesians. I have a section here on modest tolerance. It's a valid logic. It's the logic of statistical significance testing. It says P implies Q. If you observe not Q, then you conclude not P. And I talk about, the null hypothesis test. Q is what we'd expect under the test statistic. The test statistic to be under the null hypothesis. If we have what we assume is a fair coin and we flip it 100 times, and we do that 3 times, and we observe, 92, 95, and 89 heads, we would conclude that the fair coin model is not good, because we'd expect 50, we observe 89, 95, 92, which is a far distance from 50. If you want to put that on p-value scale, I don't care, but it's a long distance from what you'd expect under the model. That's valid logic, right? It's essential for falsification, good science, and it's still valid when put in probability terms. It just puts bounds on things. So Boole's Logic and Probability by Hailperin kind of talks about that. And also, bottom line is that these decisions or tests, they make room for errors. No one's claiming that the null is true in some universal sense with a capital T. Only that evidence was, for or against the null was provided with this sample size, alpha, beta, experimental design, and so forth. I'm not saying that the coin is true and I know it, like absolute terms, right? I'm just saying there's strong evidence for it. Kind of categories are mentioned, I think, in lots of these discussions. Like if it's less than 0.05, it's statistically significant. If it's not, it's not. But and so some people call this dichotomania. You're dichotomizing things. I think categories are natural in fine way observing the world, learning about the world, right? As proof of that, when I held this book up, it's not the book I wrote. It's not a blue book. It's not a book that's this thick. It's not a book on gardening, right? We know what category it's in. It's red. It's in a book in the class that Clayton wrote. It's in the book of thin to medium thickness. right? So these are categories, okay? And one way of learning about categories is Boole did Investigation of Laws of Thought. And another good book is that modern of that, well, the Hailperin book puts it in modern kind of linear programming terms. And Dave Miller has this book, The Last Challenge Problem, with some good discussion. Is that if you look at sets, you know, the thing. So Boole called this like a fundamental law of thought. He said if these are set operations, then the red book is also in the things that are red, right? So if you repeat the class, you're still in the same class. So x squared equals x is kind of how you'd write that. And you can also write that as x. The things that are in x and 1 minus x, not x, is the empty set. So things that are red, is there anything that's in the red group and also in the not red group? No. Now, we're just looking at kind of one characteristic at a time here, by the way. So, but that's what this is. You cannot have something in a class and at the same time have it be not in that class. So there's nothing that's in both of those groups at the same time. So this is just a natural way of looking at the world. Now, if you have a hard cutoff, that's not damning against frequentism. That's your decision, right? So Neyman wrote, you can separate into a region, you can separate the regions even more if you want. You can separate the region of acceptance into a region of doubt. Neyman wrote this. He didn't say use these hard cutoffs. Fisher said it's up to the experimenter to determine what would qualify for, for evidence or whatever. So for example, I could flip the coin 90 times and you're like, no, that's not enough for me to show it's not fair. It needs to be 95 heads or more to show it's not fair or something like that, right? P-values reported as a scale. The Statistical Sleuth book has that graphic. That there's a whole scale, right? And obviously this depends on what alpha is too. And again, you can interpret Bayes factors. Here's a screenshot of a study that they have these ranges for the Bayes factor. There's cutoffs there. 1 to 3 is weak. 3 to 20 is positive. What about 3.01? What about 2.99? I mean, it's the same argument. It's just what the researcher wants to do, and if you state your assumptions, I'm fine with that. But this dichotomy stuff is not just frequentism. That's anything that has this dichotomy or categories. Okay, in general, categories are fine. Obviously, there's problems if it's very strict. I think Mayo says like making mountains out of molehills and stuff like that. Where the cutoff, it's right around the cutoff, it's basically the same thing on either side, more or less. And obviously with categories in real life, if racism or any other ism is a huge problem, right? But just in general, categories are fine for learning about the world. There's nothing wrong with having a cutoff. It's how we learn things and make decisions. So reference class problem. This is not really, again, just with frequentism. You can have this with the prior. Like, does your prior represent, I've given an example of like the ability of soccer players. Is it all players, all male players, all players within a year, within a given team of a certain age? Whatever measure we do, we have to define what it's a measure of. And, Fisher pointed it out in the 30s. Venn pointed it out 70 years before Fisher, and Fisher noted that. So you could say all probabilities are conditional, but you could also just say, all belong to different classes, the reference classes. And I give an example where you can, if you're working with a North American industry classification system, and say you're doing imputation and there's not enough observations, it's a hierarchical system, so you can collapse cells to get more observations, for example. Okay. So reference class is just a part of life where if we're measuring something, we have to define what are we measuring. That's not a problem with frequentism. It's just part of the world that we're living in. Likelihood principle, the common claim frequentism violates the strong likelihood principle, therefore it's wrong. But if likelihood itself has some problems, like if you have a deck of cards and you draw out a two of hearts, likelihood would tell you it's it's more probable that the deck is all two of hearts instead of a regular deck. That doesn't make much sense. This book talks a lot about likelihood by Powhatan. So that's a pretty good read. It's also the likelihood principle has been really critiqued. Mayo has a good proof. Larry Wasserman has a good proof about Stone's paradox, where he gives an example of the likelihood doesn't distinguish four possible parameter values, but the direction of a string from a current position clearly has a lot of information in it. So a frequentist would say, yeah, we understand the likelihood principle might be a good guiding principle, maybe, or something, or a rule or whatever. But it's not, you have to take more than likelihood into account. How was the experiment done? What's test statistics being used? All that stuff is, I would call that evidence also. It's involved in your calculations, your decision, and so forth. And again, this book gives an example, a couple examples, where the confidence distributions and p-values would be different, even though I think they have the same likelihood or something. So, and the likelihood principle is violated in some Bayesian stuff too. If you're doing posterior predictive checking, some other stuff, maybe you're designing something to be unbiased or something in a Bayesian way. It violates the likelihood principle also. So it's not this like thing that you have to obey, like a speed limit or something. I don't know, some law, right? It's a general mathematical thing that is maybe a good rule of thumb, but it's not a law. So nothing in Bernoulli's fallacy talk about priors, like how to develop them, nor the problems with higher dimensions. So I don't know how the readers are supposed to digest that. How would they're just always assumed to be right or defendable, and that's just not the case. There was nothing in there talking about actually how to make one, actually how to do that. I already mentioned that as the sample size over population size goes to 1, or as n gets large, the likelihood tends to dominate your prior, so it just kind of matters less and less. And I think also hypothesis tests can serve to reject priors. There's some papers talking about Bayesian priors being brittle. Balch, Martin, and Ferguson, they look at the real world problem of satellite like colliding, and Bayesian approach is suffering from false confidence, where there are propositions that will consistently be assigned a high degree of belief, regardless of whether or not they're true. And they said the only way to now they say, and I agree, that the math is fine, but they say it's like a mismatch of the probability theory and the subject matter to which it's applied. So it can suffer, and any epistemic probability distribution, which includes Bayesian, can suffer from arbitrarily severe false confidence. And they say, which I thought was interesting, framing the problem in frequentist terms enables us to do that, to kind of interrogate the belief assignments that will be made to it over repeated draws of the data. So frequentist intervals, confidence intervals, and regions, they don't suffer from false confidence. I think that's a really strong result. Van de Schut and others look at systematic review of Bayes articles in psychology. They get more popular, but not necessarily quality. There's lots of places where they discuss this prior superficially, or they don't even discuss a prior. They have only a few reported sensitivity analysis. So these are problems. Almost probably every Bayes, if it's really dependent on the prior, would probably require sensitivity analysis. Clayton claims that basically frequentism only looks at sampling error. I think that's a very common misconception. Total survey error approach in survey statistics focuses on lots of different types of errors, not just sampling. Deming talked about that, non-sampling errors, in his book and work. Pierre Guy, I think it's pronounced. He talked about this in sampling solids, liquids, and gases work that he did. And, they do their best to try to minimize sampling and non-sampling errors. There's, frequentism is very concerned with well-designed experiments and surveys. And I think if there was a Bernoulli's fallacy, then sampling wouldn't work so well as it does. We wouldn't learn about population parameters from sample statistics. Again, assuming our samples or experiments are well designed. In fact, is this ratio approaches 1? We've sampled the entire population and we've taken a census and learned about the population parameter exactly. Again, not having any non-sampling errors. So just the fact that sampling works so well, to me, that's evidence there's no, what Clayton calls a Bernoulli's fallacy anyway. And this is a great book on sampling, by the way, by Sharon Lohr. You can check it out. This newest version is a lot thicker than the previous one, a lot heavier than the previous one. Bernoulli's fallacy book, it doesn't mention any questionable research practices at all, which is funny. It's like Bayesians, they can do no wrong. They don't no questionable research practices whatsoever. No one's fiddling with data. No one's going back, finding priors. None of that stuff, right? No one's looking at subgroups. None of that, right? Sure. Okay. So obviously that's done because we're people and we game systems and all that. So I think it's a little naive to say that, or he doesn't say it, but to not say any questionable research practices. I think you would find that too. Elsie Gould has said, non-null hypothesis statistical testing research just as susceptible to QRPs. Okay, so she has an example of a Bayesian where QRPs can go. Let's see. So there's some articles about Bayes factor hacking. Again, anything that can apply to hacking, p-values and stuff, same thing for Bayes factors or anything else. Test for non-randomness, he doesn't talk about. This book, Non-Parametric Statistical Inference by Gibbons and Chakraborty, has some good stuff. I just had to talk about the runs test here. Randomness is, pseudo-random number generators and tests for non-randomness are extremely important. Extremely, it's just getting more important with cryptocurrency, with differential privacy. It's just super important. And tests for non-randomness are great frequentist tests. And so I have an example of the run test. This is some consulting I did with my brother. He was looking at flapping nodes, which sounds like a medical condition, but flapping nodes on servers and stuff. So I have an example of that there and some test statistics. The origins of alpha equal 0.05, Fisher noted, it's up to the experimenter, right? Give some example that it comes from previous generation looking at probable error. And for a normal distribution, probable error is 2/3 of standard deviation. If you solve that, you get 3 probable errors as 2 standard deviations or a z-score of 2. And it looks at the, Q is a semi-interquartile range where like 50% of the data lies. So it was like a previous convention of statistical significance, right? But it should be based also on probability, cost of making a type 1 error. You should think about type 2 errors. You should think about the sample size. So it shouldn't just be arbitrary, but neither should kind of default prior distributions. I mean, you could say, again, about anything Bayes that's arbitrary. You could make the same thing. But there's been good science with it. I mean, it seems a reasonable first pass. FDA uses it. Some other places do too. Okay, I talk about looking at Bayes factors, and why doesn't it is arbitrary criticism apply to the looking at the Bayes factors for denoting inconclusive or weak evidence? It's just not fair. Clayton mentions nowhere in Kolmogorov's mathematical axioms is a frequency interpretation mentioned, but other critics mention that his theorems have too much frequentist baggage, so it's a contradictory, really, or up to interpretation. But he mentioned, Kolmogorov mentioned von Mises, saying that if you're going to apply going from the mathematical to the real world, which arguably is a more important world, the real world, mentions that Kolmogorov mentions the basis for the applicability to some random phenomena must depend on some form of the frequency concept, and he mentions it in a paper and then in a book. So that was important to Kolmogorov. When going from we have the math world over here, and over here we have the real world. Frequencies tend to be observable and real, so I think that's important. The book also doesn't mention any real detail positive contributions of frequentism, like sequential analysis, jackknife, bootstrap, survey sampling, quality control, meta-analysis, permutation tests, adaptive tests, non-parametric stats, machine learning, and model checking. To name some that I thought about. So I would sum it up where you can call some of this stuff Clayton's fallacy if you want, where it's just claiming frequentists only focus on sampling, claiming frequentists rely fundamentally on a weak law of large numbers, or that it's fundamentally flawed, claiming frequentists confuse, do the transpose conditional fallacy, claiming that a probability of hypothesis given data is the same as like the hypothesis given data and your beliefs, or that what you're calling the probability, in other words, saying that your beliefs is the same as the probability is not. That's not true. And also claiming that frequentism is not effective, claiming the prior of the effectiveness of frequentism or the posterior are very small, considering its positive uses, which you didn't mention at all in the book. Claiming to be able to know true underlying distributions, which nobody really knows except in simulation. And not mentioning QRPs at all with the Bayesian probability statistics. I think that's not realistic in the slightest. So to conclude, I would say, you can be coherent with probability like in Bayes, but that means you can be coherently wrong. And trying to position Bayesian probability by contrasting it against the Nazis and stuff is not a good look. I think it's, not a great argument, and neither is bragging that, Bayes can use the same tool for every task. I'd rather be flexible and open to anything. Saying frequentism is bad for science, in my opinion, is just a complete fabrication. And again, I think the success of sampling, quality control, experimental design, equivalence testing, bootstrap, that's just those little things show that it's extremely useful for science. There is a unifying logic in a frequentist approach, even if Bayesians don't realize it. It's sampling, being flexible, which critics can dismiss it as ad hoc. But I think using pre-registration, improving experimental design, allocating budget towards repeating experiments, and ignoring arbitrary journal publishing standards, they seem like sensible ways to proceed for everybody. So that's it. It was long-winded. This is the second of two videos on my webpage article, Clayton's Fallacy. But again, I say, I was not convinced by the content of his book, but I recommend the book. So check it out. I think he's a good writer. I think he's a good guy. Check out his YouTube channel. I linked to it here. And he has some videos where he explains the content from Jaynes' Logic of Science book. So I found those videos really good. And I would buy Clayton's future books. Okay. And I do recommend using Bayes' probability and stats. I've used it for small sample if I need some strong modeling assumptions. I was working with somebody on comparing just to a frequentist, a hypothesis test, because they did have some background knowledge, it turned out. So we made a prior and, I think improved the test. Missing data situations, multiple imputation, small area estimation, and then of course empirical Bayes are all methods that I've used. And again, with the frequentist, what I would call a frequentist funnel, you can take any Bayesian method and repeatedly run it and look at its error rates and stuff, and evaluate its frequentist performance. So, but anyways, I hope you enjoyed that. Please read this and vote. It's anonymous. It anonymously registers your vote. All I get is your like or dislike, and you'll see the sum of the votes. And that's all I got. So thank you very much for checking this out, and I'll see you next video. Bye bye.